All right, in this video, we're going to start Chapter 2 and talking about what we call descriptive statistics, when we have a set of data and different ways that we describe this data. So the first thing we talk about is a histogram. And so this is one type of graphic that we use for quantitative data. And it's called a histogram. It's a graph consisting of bars of equal width drawn adjacent to each other, meaning they touch each other. Horizontal scale represents classes of quantitative data values, and vertical scale represents frequencies, okay? The heights of the bars correspond to the frequency values. So frequency, remember, is the count of each data value. So if I have a -2, between -3 and -2, I have what, maybe 1 or 2 in that one bar. So it's an idea of how does our data distribute, basically. But notice on the histogram, this one is a frequency histogram, and the axis starts at 0. This one as well, it starts at 0 right there. That's the way a regular old counts frequency histogram looks like, okay? So if it's a frequency, this is what you're looking for. Now, another type is called the relative frequency histogram. And just like we talked about in the last chapter, relative frequency just means the percent of the whole that how the data falls. So if this is about cardio level, what percent of the data is between 2 and 3, I don't even know what this is, minutes or whatever. But notice that the axis starts at 0, but these are percentages. They are no longer counts on the y-axis. So you can see it more clearly on this one with the copy. But these are percentages here. Up at the top, these are actual counts, okay? But we call it frequencies. But because the second set here is relative frequencies, they are percentages. So these are percent of the whole. What percent of the data falls between these two values, basically. So it's just a relative frequency histogram. Now, graphs can be technically correct, but they can be misleading. And so two common types of bad graphs are what we call non-zero axis graphs and pictographs, okay? Non-zero axis graphs are exactly what you would think, okay? It means that the y-axis does not start at 0, okay? Some graphs are misleading because one or both of the axes begins at some other value than 0. So the differences, what happens is the differences are exaggerated. You can't really see the difference, okay? This one, this right here has been adjusted, so you can see the difference in the relationship when you have the 0 at the origin, basically. So the placebo is not as ineffective as it appears on this first graph, okay? So a non-zero axis is one issue. The other one is pictographs. These are drawings of objects that are often misleading. Three-dimensional objects are commonly used to depict data, but drawings of such objects can create false impressions that distort differences. For instance, look at this. You could use the cigarette and the shading to show different percentages. However, because they made this one so much larger than this one, it's deceiving. It shouldn't be like that. They need to be the same size and the shading be changed in order for it to be accurate to the eye, because your eye is going to think it's something very different when it's really not that big of a difference. Now let's look at the next page. So let's look at a histogram and how would we read this, okay? An experiment was conducted in which 2 fair dice were thrown 100 times. The sum of the pips, those are the dots, showing on the dice was then recorded. So you have 2 dice, you've added up what they come up. You know, like a 6 and a 4 adds to 10. The following frequency histogram gives the results, all right? So what was the most frequent outcome of the experiment? Well, which sum happened most often? So you would look at the peak, okay? That would be an 8. What was the least frequent? Well, that would be a 2. Easy enough. How many times did we observe a 7? Well, here's 7, and I look at the bar, and since this is frequency right here, it's just pure counting. So how many times did we get the sum of 7? We got it 15 times. How many more 5s were observed than 4s? So for 5s, I have, I don't know, around 11. And then for 4s, I have maybe 7. So I subtract it. many more? That would be a subtraction, so I have 4 more 5s than 4s. Determine the percentage of times a 7 was observed. So I'm going to look at the total out of, or how many times I got a 7 out of the 100 rolls, right? Because it tells us they did it 100 times. So look at my 7. I have 15 out of 100, which gives me 15%. All right, that's all of 2.2. It's really fast, pretty simple. So we're going to jump on into 2.3, 2.4, and look at how we handle a list of data. All right, the first thing, you know this word, you've seen it, is median. The median is the middle value when the original data are arranged in order of increasing or decreasing magnitude. Okay, the median is denoted by a capital M. If the number of data values is odd, the median is the number located in an exact middle. If the number of data is even, the median is found by computing the mean of the two middles. And I'll demonstrate this in a moment. So let's look at this. Determine the median with an odd number of observations. So here we go. In this data table, it represents the length in seconds of random sample of songs created in the 70s. Find the median length of the songs. So first thing I have to do is list these guys in order from least to greatest. So I'm going to pause the video and do that. You do it on your paper, and then we'll check in a moment. All right, so I've listed them from least to greatest, and I just need to find the middle. So I just go from outside to inside till I find the center. It's an odd number, so there will be one right in the middle. Easy enough. So the median is 217. Simple as you can get. Now, let's look at what do you do if there's an even number of observations. So again, we're going to need to list these guys from least to greatest. You can do this with me if you'd like. It goes 62, 68, 71, 74, 77, 82, 84, 88, 90, and 94. Now, it's even, so if I start doing this, I end up with two values in the center. So what I have to do is find the average of those two. So I take 77 plus 82, divide by 2, and I get 79.5. So that is my median for this set of data. If it's even, that's what you got to do. Now recall that the median divides the lower 50% of data from the upper. So it's like half and half. 50 is lower, 50% higher. Right? This is a special case of the general concept of percentiles. Now, a percentile is denoted P sub k with a value in a set of data such that k% of the observations are less than, here it is, or equal to that value. Okay, so like at the median, it's 50% is less than or equal to this value. So it's really simple to find percentile. A number of values less than x divided by the total number of values, and you multiply by 100 to make a percent. It's pretty simple. Now the percentiles are used to give the relative standing of an observation. Like where does it fall in the list of distributions? Many standardized exams such as the SAT, college entrance exam, use percentiles to provide students with an understanding of how they scored on the exam in relation to other students who took the exam. So like if it said you're in the 77th percentile, that means that you scored, that 77% of the people scored less than or equal to how well you did. So it's pretty decent relative standing. A special case of percentiles is what we call quartiles. Okay, think quartiles like quarters. Okay, they're in the 25s. Okay, so quartiles divides it into fourths. Okay, so 25th, 50th, and 75th percentiles. And we denote them with a Q1, a Q2, and Q3. So here's 25, here's 50th, and 75th percentile. Okay, as simple as it can be. So if I have this set of data, and my minimum value is here, my maximum value is over here, I find my median. My median is also known as my Q2. It's the 50%. So then I take what's on to the right of the median, between the median and the mean, and I find the center here. This is the Q1 or representing the lower 25th percent. Here's another 25% that lands us at 50% by the time we hit median. If I go another 25%, I'm at Q3, or the 75th percentile, and the last 25% brings me all the way up to the maximum value of that range of data. Now, the interquartile range is the difference between Q3 and Q1, and it describes the variability of the middle 50% of data. So if I take all the data, where do things kind of vary between in the middle? It's a really simple equation. You take that Q3 value and you subtract Q1, and I'll show you how to do this. Here's your steps though. First thing you have to do is arrange the data in ascending order, least to greatest, okay? Has to do that. Now, determine the median, find the middle, and then, or the second quartile. It's the same thing, median, second quartile, same thing. Now, to determine the first and third quartiles, Q1 and Q3, by dividing the data set into two halves. The bottom half will be the observations below the location of the median. Top half will be the observations above. I'll demonstrate in a moment. The first quartile is the median, if you will, the median of the lower half. Third quartile is the median of the upper half. Average the two values if you have to, okay? Just like I've shown you before. So let's try this. The Highway Loss Data Institute routinely collects collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. The data in the table below represent a random sample of 12 collision coverage claims based on the data obtained from the Highway Loss Data Institute for 2004 models. Okay? Find, interpret the first, second, and third quartiles for the collision coverage claims. So like I said, the first thing you have to do is list these in order from least to greatest. So to save time, I kind of worked off screen and did this, but they go in this order. So I'm going to write kind of small, 189, then it goes 370, 1185, 1414, 1953, 2332, 2336, 3461, 4668, 6751, I'm gonna run out of room, 9908, and then lastly the 21,147. That must have been a bad collision. All right, listed in order, but there's 12 of them, so I have to think through finding the median. Okay, so start finding the median first. So if I go in 6, 1, 2, 3, 4, 5, 6, here's 6 and 7. To find the median, I need to average these two values. So I take 2332, my calculator, plus 2336, divide by 2, and I get an easy 2334. That's my median, okay? It's also Q2, right? Now, that's right there. Now to find Q1, I need to find the median of this lower half of my data. So again, it's an even number. So I'm going to take my middle two and find my Q1 right here, but I have to average those. So I do 1185 plus 1414, and then add them, divide by 2, and I get 1299 and a half. Then I'm going to repeat the same process for the upper half of the data. That would be these two. The average here would be my Q3. When I average those two values, I get 5709 and a half. All right? So there you go. So Q1 is 1299 and a half. Q2 is 2334. Q3 is 5709 and a half. All right? To interpret, I would say this, that 25% of the data is less than or equal to $12.99 and a half. For Q2, it would be 50% of the data is less than or equal to $23.34. And then for Q3, 75% of the data is less than or equal to 5709.5. That's how you interpret it. It's really simple. Now it says determine and interpret the interquartile range. So IQR, remember, is Q3 minus Q1. So I just take my Q3 value, 5709.5, and I'm going to subtract Q1, 1299.5. And I get 4410 even. So to interpret, I would say the middle 50% of the data has a range of $1410, okay? That's the range of the middle 50% of the data. Now, something we called a 5-number summary is a subset of the data that consists of the minimum, the first quartile, the median, third quartile, and the max. So it's a real quick summary of the whole set of data. So it's the min, Q1, the median, Q3, and the max. Because remember, median is still Q2. All right, so these are the 5 numbers you need to know to see the distribution of data. Now, a box plot is also called a box and whisker plot. It's constructed from the 5-number summary. It shows how far extreme values are from the bulk of the data, the middle 50%. So the strengths of a box plot, it gives a direct look at the location and the spread. Outliers are identified, and it's great for comparing. Now, weaknesses of this is that symmetry and skewness cannot be judged, which we'll talk more about that in a minute, but not so much shape. You don't really know clear shape when you look at this distribution. Again, we'll revisit shape in a little bit. When performing any type of data analysis, we always want to check for extreme observations in the set of data. So an outlier is a data point that is not consistent with the bulk of the data. These values can occur by chance, because of error in the measurement, data entry, or just from sampling errors. So I'm going to walk you through this. So here's how you do a box plot. Here's your step-by-step instructions. Determine the first and third quartiles, okay? Compute the IQR. Determine the fences, okay? The fences serve as the cutoff points for determining outliers. So to do this, you have to take Q1 and subtract 1.5 IQRs. Upper fence, you take Q3 and you add 1.5 IQRs. Step 4, if the data value is less than the lower fence or greater than the upper fence, it's considered an outlier. All right? Now, here's the way it looks. When you do your box, notice this edge of your box is Q1. This edge of the box is Q3. This line right here is the median. Now, this ends right here. It's the smallest data that's not an outlier. If the minimum is not an outlier, then it's the minimum. Okay? Same thing up here. This is the highest data point that's not an outlier. So in this example, this one had 2 outliers. So what you do is you take those 2 outliers, you put stars out here, and then you take the next highest piece of data, and that ends the whisker right there. So let's look again at our data that we just completed about the collision repairs. And I'm just going to rewrite what our 5-number summary was. We had 1299.5 for Q1. Q2 was 2334. Q3 was 5709. Now the max was definitely this 21,147, and our minimum was the 189. Okay, so there's our 5-number summary. And what did we say? IQR from the previous page came out to be 4410. So the first thing I have to do is find the outliers of the data. So I do a lower fence, and I'm going to do an upper fence. So to do the lower fence, I have to do Q1 minus 1.5 IQRs. All right, so Q1 was $12.99.5 minus 1.5 times 44.10. If I run that number, I get a negative 53.15.5. Well, that means negative money, like the collision people actually gave them money. That's not going to happen. We don't have any values in our table less than 0, so there's no low outliers. For the upper fence, I start at Q3 and I add the 1.5 IQRs. So Q3 was this, 5709 plus 1.5 times 4410. And I get 12,318. Well, that's the fence. Do I have any values in my table higher than 12,000? So let's see. Definitely 21,147 is a high outlier. Okay, so sorry about that. So then to draw my box plot, I'm going to have to do some creative scaling here because my axis needs to go so far. So like 180 is way down here, and we'll do like 22,000 up here. So we're just eyeballing it. I'm not going to be worried too much about being OCD about your box plots, but I always recommend you start in the middle, at the median, okay? Median is at 23.34, so it's about right here. Q1 is at 12.99.5, so that's probably right in here, and this is here. So I can label and my lower, I had no low outliers, so I can draw the whisker to the minimum, which was at 189. All right. Now, we determined on the high end that the 21,147 was way up here. It's an outlier, so I kind of put a star. Then I look at my data, and I eliminate that point and think, what's the next highest value I have? Well, that's the 9908, which would probably, I don't know, be right here. Again, don't get OCD about it. I just want you to know what those values represent in the distribution. Okay? Now, one more thing and then we'll be done with this video, I promise. Use the side-by-side box plots shown to answer the following questions. All right? To the nearest integer, what is the mean variable of x? So x is this top distribution. So median, remember, is this line. So I'm just going to look straight down, and it's around 15. You see enough? This is x, this is y. B, what to the nearest integer? What is the first quartile of variable y? Well, remember, this is Q1 right here. So I read straight down, and it's around 22. C, which variable has more spread or variability, and why? Okay, so when you think spread or variability, you can think range, or you can think IQR. Either way, range is min minus max. So here's x, here's y. Let's figure this out. The range of x goes from what, 30 to around, I don't know, 4, so that's 26. The range of y goes what? 39 minus maybe 8. All right, so it looks like y has a higher range. Look at the IQR though. Q3 minus, remember that's Q3 minus Q1. So right here, what's that about? 21 minus what, 11? And on y, this goes from about 34 to 22, has an IQR of 12. So either way, both values here for y have a wider range of values, which is more variability. So y has more spread, is what we call. And then D, Does the variable x have any outliers, and what's the value of it? Well, hopefully you see that star right there. That is an outlier, and we're going to approximate the value of that outlier at about 29. We don't know what this is in this problem, but that's about what it is. All right, so the idea is you have to be able to read a box plot and know what these lines represent, okay? You're not going to spend a ton of time creating it, but you got to know this is minimum Q1, Q2, Q3, and maximum unless there's outliers, okay? We'll talk more about this in class, but hope that made some sense to you.